Hi everyone. So this is part 2 of kinetic energy discussions. So far we've seen that kinetic energy looks like it is equal to a half mv squared, and the units for it is expressed either kilograms, meters squared, seconds squared, or newtons times meters, or we would call it joules if we like. And then I compared kinetic energy with momentum. Just like momentum that has this velocity in it, where this velocity is subjected to a lot of changes. So change in velocity gives rise to change in momentum. And we learned about that. We learned that change in momentum is the force exerted on it that gave rise to the change in velocity times the time over which the force is exerted on it. The same thing pretty much applies to kinetic energy, because kinetic energy is also dealing with velocity in its formula, and this velocity is not necessarily the same at all times. Velocity changes. Something is at rest, I push it somewhere and it starts moving. So it starts having some kinetic energy. So change in kinetic energy is also dealing with, some exerting force on it. And we know it from Newton's first law. As long as you have change in your velocity, that change in velocity means acceleration. Acceleration means some force is in play. So we know that we expect that change in kinetic energy, which is basically because of the change in its velocity, has to deal with some force, right? So let's just see how things are with this picture. Suppose there is a block with mass of m, and it's sitting at rest, so it's not moving or anything. Hence, its kinetic energy is 0. Now, if I push the block towards the right, the block starts moving, and now it's moving. So now it has both the mass and velocity. So hence, it has some kinetic energy. See, the kinetic energy changes. So now, like first, initially it was 0. Now it is a half mv squared. Change in kinetic energy obviously deals with my force pushing it to the right. And also my force made this guy, basically got this moving by d meters, right? And it turns out that change in kinetic energy is essentially the exerted force on the object times the displacement that this force is doing on this object. And we call this work. So just like change in momentum was impulse, and that was exerted force times the time that was this force exerted on the object, change in kinetic energy is work, and it's essentially the force that's exerted on this that made the change times the displacement over which this force is basically moving this to the other direction, to somewhere else. Now, units for work is equals to work equals to change in kinetic energy, and you see work is force times the displacement of the force, so it's newtons times meters, and that is the same as joules. So let's just make this complete. Change in kinetic energy, we'll learn that this is work, and that makes a lot of sense. If I'm actually doing some work with my exerted force, I'm moving this to somewhere else. This means work is done on the object, right? So, and this work is basically the force times the displacement of the force, and it causes kinetic energy to change. See, it was at rest and now it's moving, right? So there are different ways of, forces and the displacement of the of objects are in different ways. So let's just elaborate on that. Well, suppose there is a block here and I'm pulling it to the right with my hand, and I have the mg at all times. I have support from the floor, and there is at all times I have this frictional force. So the free body diagram is essentially dot mg, the second ingredient, and then what is in direct contact with the block. So it's the floor, so Fn and Ff, and my hand, which is F of hand. So this is the free body diagram of the block once the block moves this way, because my hand is pulling it. So the block basically is now moved this way with a distance of d, right? So let's now see what each and every one of these works are done by each and every one of these forces. So I'm measuring the work done by each and every one of these forces as if the other ones is non-existent. So the work done by my hand, work done by force of hand, is my force of hand that actually does the work, because if the block is here and I'm pulling it that way, I know the block basically obeys my order. It actually moves along the direction of my force of hand. So that's this. Now, how about frictional force? Work done by the frictional force here is the frictional force times the displacement. But as you can see, the block, although it moves to the right, at all times the frictional force is to the left. It's as if the frictional force is at all times resisting against the motion of my block towards the right, and it's just pulling it at all times to the left, trying to resist against this motion. Whenever there is this situation where displacement is one way and your exerted force is the other way, so they are actually anti-parallel, the work is negative work. And it makes a lot of sense, because we know that all in all, work is changing kinetic energy. Now, if work is positive, it means that kinetic energy gets bigger and bigger, because this changes kinetic energy second minus first. So if this is a positive number, it means this is bigger number than that, which makes a lot of sense, which makes sense that my block is now moving compared to being at rest. So kinetic energy is growing and growing, and that corresponds with a positive work. Whereas for negative works, if work is changing kinetic energy and it turns out to be negative, then it means that kinetic energy second is actually smaller than the first, which it actually makes sense, because it's the frictional force that resists against the motion. It tries to stop it, so that the second kinetic energy at all times becomes smaller than this, and that's why the work is negative. Now, how about these forces that are right angled? They are orthogonal to the direction of motion. See, the block is moving to the right, but at all times there is this mg that's pulling it down. But the block it's not even listening to it. See, the block is going towards whatever it wants, wherever it wants, and however there is this mg acting on it at all times, pulling it down, but the block is essentially not even listening to it. So whenever your force, now force of mg and also force of normal force, both of these forces are perpendicular to the direction of the displacement. So if that ever happens, the work is dead zero, because it's as if the block is not even listening to these orthogonal forces, these right-angled forces. See, your displacement is here, but at all times I have mg. So this is 90 degrees angle, and it's as if the block is actually moving without without hearing the voice of this force. Also, it's the same scenario for the work done by the normal force. Is the same thing. It's going this way, but at all times something is pulling it up, but it's not even listening. It's not even going up, right? So these are the three different categories of works with respect to, with respect to their forces. In the next video, I'll talk about more examples. Bye-bye.